Hello everyone. I'm sure you are doing awesome. This is the very first video of the networking internals. So the prerequisite of the video is some a very basic prior knowledge of OSI model. If you have no idea on what OSI model is, I have discussed it in real detail in my OS internal series. That is the last video of the OS internal series, in the sixth video to be precise. You will find all the discussion. Please go through it, if not the whole, the first 25 minutes, but it is recommended that if you go through the whole video, which is probably 1.5 hours long, it probably will give you a very good idea around how the operating system socket management is happening, and multiple networking related concepts that have been discussed there, which you will be able to link very well when you come into this video. So this is a bit of a internal course, and the motivation for this video or the video series is not from the core network engineer perspective, but it is more from a application engineer perspective. Like when we are making certain database calls, what exactly is happening, the database suppose in a different network, when couple of different network systems, when they are interacting, what exactly is happening at that point of time. Those sort of details are not very much explored by the application engineers, but they are very much required whenever any major issue comes, or suppose whenever we are getting some sort of a HTTP status code. We don't really know whether it is coming from the application layer or the network layer, or what is the exact team that we should be reaching out to. Maybe it's a DevOps related issue, or a SRE related issue, or some network engineering issue. So once we are done with this whole series, we will be able to completely visualize end to end what exactly is happening for a given particular request that I am sending it from my application. So again, just to reiterate, the intention behind this whole lecture series is from the engineering perspective. When this host to host communication is happening, what exactly going internally? Okay, that is something that we are going to explore. So before going into further details, the first thing whenever we are talking about any sort of networking concept in day-to-day application engineering, the thing that come into our mind is definitely like a IP or a host machine. Okay, so if I just ask you what exactly this IP represent. Okay, so suppose there is a certain IP I have given you, and the question is, what does it represent? So an IP, the first answer probably will come from you. An IP represent one machine in a world wide web or in a network, right? So it is not only identifying a machine or a device. Okay, so this is a very important or very major concept that we should understand. A IP doesn't only define a machine or host. So what does it define? It actually defines host plus network. Now you might be wondering how. So often when we are looking into our IP addresses, we will see things like this. There is a subnet associated with the IP. So in this particular IP, it is actually comes with a subnet. Without subnet, there is no value of a given IP. So again, just to reiterate, an IP address without its corresponding subnet mask, I will just write it down so that we keep on reiterating and it gets fixated into our mind. IP address without corresponding subnet lacks I don't know, lacks fundamental information, fundamental identification information in a given network. Plenty of spelling mistakes. Okay, so why it is so? The way we will proceed, it will be clear over the time. Okay, so when we are having this 24 subnet, this 24 subnet is basically how it is to be represented is it is to be divided into three parts of 8. So how it is actually divided is, so suppose we take this number 24 and there are multiple parts will be to it. So how these parts are is 8, 8, 8 and 8. It won't go beyond 8 for sure. So suppose if the number is 32, how it will be? Sorry, it won't be 8, the last one will be 0. If the number is 32, how a subnet is being divided? A subnet is being divided as 8, 8, 8 and 8. Okay, so this is how we are going to divide if the subnet is 32. Point to note here that 32 is the this is the highest any subnet can be, and further while representing it, how do we represent these numbers? We represent it in terms of 1. Okay, so 8 will be, there will be 8 ones will be there, also here also there will be 8 ones, here will be 8 ones, and this will be 0. And so end of the day it is being represented as something like in binary like this. Now if I tell you that this binary again I need to convert it into a decimal, then how it would look like? So the decimal form of this will be 255.255.255.0. The decimal form is not 8.8.8.0. I just divided it for your understanding. Like, we are not going into the detail of how the subnet is being calculated, but just understand this represents the mathematics how a IPv4 address to be interpreted. So 32 bits in an IPv4 address are used for network portion. So sorry, I mean to say not 32 bit, 24 bit will be used as network portion. So what was our IP? Our IP was this one. Okay, our IP was this one, and in this 24 bit is still this part 8. So how it is being calculated is this is 8. The next one, the 168, is also 8, and this 1 is also, this will represent 8 bits. So when I'm talking about 8, like this is basically 8 bit, 8 bit and 8 bit. Okay, so total 32 bit, and this part is representing the network. So here total, sorry, total 24 bits are there from here to here. How many? Total 24 bits are there, and this 24 bits represent the network bits, and this 10, this 10, this represents the host. Okay, so how do we how are we exactly interpreting then? For 24, subnet, we understand in this way that there will be 24 network bits plus 8 host. For 16, it is like 16 network bits plus 16 host. So had it been like this, it means that this part will be network and this part will be host. Okay, so this is the network part and this is the host part. All right, so the full IP address, the first one that we took, 192.168.1.10, it represents something like device 10 on network 192.168.1.0. Okay, so it is the device 10 on this given network. So if we are understanding till this part, this is enough. So how exactly the subnet is being calculated, how the operations, like the other operations with the main IP is happening, we do not need to go into the detail, but just understand this thing. Without a given subnet, there is no value to the IP address, and the moment we know the subnet, we can identify the network and also we can identify the host. How? Any subnet that we get, whatever the numbers that will be there, that will represent network bits and the rest of the number will represent the host bits. So I think we are clear till this part. So now let's see this concept into action. Suppose we are typing something like facebook.com in our browser. Okay, suppose this is the origin machine is where me as a user is there, and then there is a target which is suppose the Facebook server, and this is my own router. Like these are the very basic components everybody is aware of, so I just wrote it there. So suppose in my browser client I wrote something like facebook.com. So what happens at the very first level is there is something called domain name server resolvers are there. Okay, so ideally this request through the operating system's TCP IP stack goes to the DNS or the domain name server and gets the IP of the target. So suppose in this case my origin IP is something like 168.1.5 and my subnet mask is something like this /24, and then once it goes to the DNS, the destination IP is also determined. Suppose the destination IP is something like 31.13.66.55. Okay, so now I know that my current network is the first 8 digit is my current network. Okay, because it is 24, so 24 as we have been interpreting it in that way that there are uh, in eights it gets divided, so the network is nothing but the first 3 component of the IP address. Okay, now from here one thing I can easily say that they are not in the same network for sure, because none of the component matches here. They are not in same network. Okay, we can conclusively say. So the moment we find that this is not in the same network, what happens is this particular packet or this particular message, so this particular message that I have been planning to send from here, what happens is it then goes as a request to the router, and router determines that where exactly it need to send it. How it determines? So suppose this is my router, and what exactly is router is, this is the exit point from local to World Wide Web or any other external network. So for the time being, let's take it as a World Wide Web only. So router is the exit point of World Wide Web. So one of the very important component that router has is called router table. Now router table will comes to rescue, which generally holds all the destination IP addresses actual uh, details. So what happens over there is what this router does. So the first thing it does is it extracts the destination IP from the packet. Okay, extracts the destination IP, and what exactly the destination IP? This part is our destination IP, this whole thing. Okay, and once it extracts it, then it consults something called a routing table. Okay, so there is a table. This table just hold like which network and what is going to be my subnet, all the details for a given destination it holds. Okay, and then it try to find the best match out of it, and once in the routing table it find the match, what it does is it forwards the packet to the next hop. So one more important concept here is, like, when I'm sending it something from India, suppose this is India and this is USA, if it is a direct like origin to target connection is there, then ideally it goes through this kind of wire cable which is inside the sea. Okay, so the optical fiber cables that we through which the data actually travels, it is under the sea, and this is one of the Google's network which is being fixed by, like, there were some problem in that optical fiber line, and what exactly is being done here, some kind of a repairing is going on. Okay, so you can you can imagine how grand the whole scale is, that this origin to this target is going through from this huge optical fiber cable under the sea. So this router cannot is unable to send directly to the target, because there will be so many in between hops will be there. Maybe some hops will be there in, like, suppose you are sending it from Bangalore, maybe some hops will be there in Mumbai. From Mumbai, like, it will probably go to Dubai. I don't know, like, how we travel through flight, it is in the same way. So what would happen is this particular router will have, there will be so many internal router before we send our data to the target. So what would happen over here is it will consult the routing table and it find the best match, and then it will forward to the next hop. So all these places we can call as a hop. Okay, so it will keep going from one hop to another. Okay, like one hop to the next hop, and gradually after every hop it goes, it keep on checking whether it is coming to the actual destination or not. So our router will determine what is the best route, and through this route all the routers will keep on forwarding to the next best possible route. And then what happens is gradually through all of these things, like from here, then it will go from here to there, it comes to the actual directly connected internal meta network, and then it determines that the destination IP, whatever that 31.13 and 66 dot 55 that we have, it is part of this network. So in this network, probably the probably in the machine number 55, I'm going to put my data into. Okay, so this is how the whole packet to packet communication happens. Now here one of the important concept is default gateway. So what exactly is default gateway? It is nothing but the IP of the particular network router. So default gateway is my gateway or the exit point to the World Wide Web. So the IP of this router is being called as default gateway. So what exactly happens over here is, in case during this communication it finds that they are not in the same network, it sends the data to the router, or another language is default gateway. So when we are saying that it is not in the same network, we are sending the data to the router, that means that we are sending the data to the default gateway as well. So I hope till this part it is clear to you. So now that we have the idea how exactly the data travels once we put facebook.com into our browser, there are one or two more important aspects that we should be looking at as well to gain the complete understanding. So one of the important thing is called ARP, or address resolution protocol. Okay, so what ARP or the address resolution protocol is, we will take this example and we will try to understand this. So uh, while concluding this part, we discussed that uh, the moment we find that the our destination IP is not same as our origin IP, or the destination network is not same as our origin network, so we have to go to a separate network. And in that case, the default gateway will come in our rescue. So we know the default gateway, but understand one thing, that without knowing the MAC address of that particular router, we will not be able to forward our network packet. And ARP, or the address resolution protocol, help us in that. So what is the role of ARP here? So what ARP will do is, once we find that it is not in the same network, ARP is going to broadcast the request and ask. So like if I just write it over here, so what ARP will do is it will broadcast the request and ask who has the MAC address of my default gateway. So once we get the MAC address, like MAC address will be something like this. Okay, so this ARP, whatever we are seeing over here, MAC address, it will return something like this, and then it will hit that particular default gateway using this MAC address. So that is the role of our address resolution protocol. So this is also one of the important aspects of our network communication. So we can now formally try to conclude how the whole communication happens. Okay, so the communication happens in this way. It starts from the browser. We will just go now by component by component. It starts from the browser. In our browser, we write something like we need to go to the facebook.com, right? So in our browser, we will write our client or the facebook.com, and what will happen is this will at first go to the operating systems outer or the send queue, where the TCP IP connection will be first attempted to attempted to get connected. So we will again go into all those details, but just understand that operating system is the one who does the part of DNS lookup. Okay, so operating system will come in play here, and what it will do is it will do the DNS lookup. So it will go there, it will do the DNS lookup here. Okay, so once the DNS lookup is done, so what would happen is it would return us the actual destination IP. So now for the facebook.com, probably we will get the actual destination IP as we discussed earlier, something like this. Okay, and then it will check whether this destination IP belongs to this, whether this destination IP belongs to the same subnet or not. Okay, so it checks the same subnet, a question it will ask. Okay, so if the answer is no, what it will do is then it will go to the ARP. So from here it will go to ARP. ARP would look like something like this. Here you see, this, right? So what ARP will do is ARP will broadcast the request, and it will get the response from the router itself that my MAC address is so and so. So what ARP would do is ARP would send a broadcast ARP request. So we can just call it as a broadcast. So this is basically ARP request, and this is a broadcast. ARP broadcast, and ARP broadcast will give you the given MAC address. Suppose the MAC address is something like this. MAC address will be returned over here, right? And this MAC address will be put to our operating system as well. So what would happen over here is, if you look carefully, our packet was sitting here. Okay, all these things are going on, our packet is still sitting here. So now that we know from the operating system end that where exactly that I need to send my packet, so there what I will do is from the operating system, like this will actually come till the operating system layer. Okay, this will actually come to the operating system layer, and now the operating system knows that it can it can send this particular packet to this router. Okay, so now after getting to know this particular MAC address of the router, it will send it to this particular router. Now what would happen? Now from there, router will actually take it to the ISP or the internet. So now the www or the internet will be opened for this packet, and in the internet the router will take, after this step, the router will take this packet to the internet, and then the internet will go through the various network hops, and then at the end of the day what would happen is it will reach to the Facebook server through this internet, as we were talking about, like through the optical fiber across the globe. It will reach to the facebook.com, and then facebook.com will send the proper response as per the request. So after this it will keep on sending the response on this levels, the responses will be sent. So all the requests that will be coming, so this is the packet, this is also the packet, and here our response will be sent back. And of course, like via each layer, it will similarly be taken into the to our operating system, and then the operating system will hand it over to the our browser. Okay, so I think this part is now clear to us, like the complete picture. We have spent good amount of time on this just to understand what exactly happens behind the scene for a certain request. But few of the further interesting thing that I want to emphasize in this process is when we were discussing about uh, our OSI layer. So if I just tell you, or if I just ask you what exactly happened from the OSI layer perspective here. So from the physical layer, so from the physical layer that we have, so of course it will go to the data link layer, that is where it goes to the router and then it goes to the main network. Okay, so physical data link and then the network. This part is clear to us, right? Now, where exactly it travels? If you just see clearly, it travels through the, once it goes to the network, it travels through this optical fiber, right? And time to time, it will get into this kind of routers or hops. So suppose the thing is, it will go to the wire like this, and then again from the wires it will go to some kind of a hop, and then what will happen is it will again tell you that okay, now go through a different path. So for example, my traffic has to travel from India to USA Facebook server, right? So suppose at first it goes to Dubai, and from Dubai it will tell that take this optical fiber route to Africa. Okay, and then again from Africa you go to the southern part of the America, or you go to Chile, and from Chile then you go to the actual United States. So what would happen is the router will keep on redirecting the traffic one by one using its router table. So what exactly happens is there is a hop that runs that physical data link network, and after the network also again the hop will be something like this, again physical data link network. So this will keep on happening, and at last when it reaches to the Facebook server, then again it will go through all the way to the application layer. So in between, like when it originated from the client and when it goes to the final browser, so in between this hop keep on happening. So if I just write it here, it is something like this. I will, okay, so just to explain again, what exactly happen is my browser will send it to the app, then from there the presentation layer, then the session layer, then the normal transport layer, network layer, data link layer, and the physical layer it will go. Okay, and after that what happens is this physical layer again it will take you to the data link layer, the network layer, the data link layer, and the physical layer. So physical layer means the wire it completely goes, and the data link and the network layer is the collectively we can say that this is the router. Okay, so again this part is basically our router across the various countries, and the physical, this is nothing but whenever we see physical, whenever we are talking about the physical layer, that is the actual optical fiber line that is goes through. Okay, so I hope it is now clear to you how a end-to-end communication happens across the network, across the global network. Okay, so now when this particular packet is traveling, so the the way it travels is as something called IP packet. I think we already discussed that. So IP packet has some very interesting components which are very much essential for us to understand. So the first one is definitely the origin, like from where it is starting, and then there is like origin, or the even I can say something like a source IP rather. I think that will be more accurate. Then there is something like a destination IP. Then there will be TTL. Then there will be DF, or the don't fragment flag. We will come on to everything. Okay, and then the protocol. So we will just go one by one to understand what are the components of a IP packet. So source IP and the destination IP, I'm pretty sure that these are the two things that it is already clear to you, like what is source IP and what is destination IP. So what is TTL? TTL, if we go by like normal computer science terminology, it is basically time to live. But here again, computer scientists were not very good in naming these things. So it is basically not the time to live, it is basically the number of hops. So as we were talking about, like when it goes to this cycle of data link layer, network layer, okay, physical layer, data link layer, network layer, again and again through the router and uh, through the optical fiber layers across the internet, what happens there is this all things are being called, like every single physical data link and the network layers combination is being called as hop. Okay, so this terminology that you see hop, it comes from there. So the number of hops the packet can take before getting drop. Okay, so the number of hops a packet can take before getting dropped. So suppose there are too many hops are there from India to some remote location of Romania. Okay, then what might happen is it is taking, suppose like the allowed hop is 32, but it is taking more hops than that maybe 41 hops. So after 32 it will already be dropped. Okay, so whenever you are pinging some IP, you will always see, like in case you are using a Windows laptop, just try any IP by writing ping. There you will get this TTL details as well. Okay, and in case you want to see what is happening for a complete request, like when we are creating the request from our end and how exactly it is traveling through the internet, then in um, the there is a very useful command that is being there, that is called trace route. Trace route is for Linux systems, and for Windows system there is something called traceart. Okay, so if you just write something like traceart facebook.com, okay, if you just write something like traceart facebook.com, it will give you some sort of a output like this. We will just discuss this output with some little detail, but the point that I'm trying to make is, it is what it is doing is, this traceart command is, it will give you from your client machine tracing the route to the whole facebook.com. So I think it is around some 30 hops is the maximum allowed one. So if you see over here, if I just have to explain it to you what is happening, you see at first it is going to the network layer, then it goes through the network card. Okay, then there are different hops and how much time it is taking into each of the hop before it reaches to the edge star mini shv. Okay, So now we got the idea that what exactly a TTL is. Okay. So now let's again concentrate on the next thing, that is called don't fragment. Don't fragment is nothing but a flag which tells that do not split this packet into smaller pieces. So what generally happens is, like, while sending the data over the wire, if the packet is little too big, it keep on sending it keep on making a segmentation around it, and once it is received at the final server end, it again joins all of them back. So this part tells that don't fragment. It is not very necessary for the application developer concept, but just a good to know things. The important part that we have here is the protocol field. So protocol field we will definitely explore in a uh, much more further details, but just know for the time being what this protocol field does is, like, if you examine any packet, you will see that there are some flags around the protocol. So something like, if it is 1, that means it is ICMP. If it is 6, that means it is TCP. And if it is 17, that means it is UDP. For the TCP and the UDP, we will we will do the deep dive later in some other video. Okay, so example, like, just to give you some idea what happens in our request to Facebook, it is a TCP request. Okay, so in the protocol field you will see that 6 will be there. So when the packet reaches the Facebook server, the operating system looks at the protocol field. It sees it's a TCP and passes the load onto the TCP stack of the particular server. So that is why these flags are important to maintain. And now, how TCP stack works, how UDP stack works, we will definitely come into, like, way more deeper details into our coming videos. In this video I'm not taking this thing into the scope, but the ICMP, I will let's discuss ICMP with a little bit more details, because we will not probably come back with the ICMP. But ICMP sometimes become really important for the application engineer, when and in which use cases we will discuss. Okay, so when we are talking about ICMP, ICMP is nothing but Internet Control Message Protocol. Okay, now, when is the ICMP is used in application engineering? So although it is not directly used, but ICMP powers many network tools and diagnostics that which are critical for application reliability. So it is like the tooling for app reliability. So whenever we are looking for some kind of a network reliability in application and we use this. So I will just put this code and try to explain what is happening over there. Okay, so here you see that I need to understand that whether my particular host is reachable or not. So if I just make a TCP call there, so TCP, you know that there is a so many other things are happening around that, like that there is a TCP, there are things like TLS, and it is a three-way handshake and a four-way tear down that is happening. ICMP gives us a really easy protocol to determine whether that host is reachable or unreachable. So this is one of the Python code. In this Python code, what we can do is we can use this function of ping. You can see, like, the operating system is making this system call, and we can ping anything using this method that we have written. And what it will give us is, it will give us the test connectivity around it. And also there are something like the tracing the network path and some other thing, some other tooling we can do using ICMP. So whenever we have to uh, get some idea around whether the network is really reachable or not, probably we will use ICMP in this case. Okay, ICMP is one of the better alternatives than using the TCP connection, just for checking the connectivity or the ping request. So when we see now, like, let's explore a question like when we see something like a destination unreachable, does our client like C sharp HTTP client sends ICMP packets? No. So we have to understand that in our application end, whenever we are making those kind of client calls, okay, so when I say client call means suppose we are writing something like HTTP client dot send async, okay, and we are just some URL we are calling. In this case, we are not making a ICMP call, rather it's a totally TCP call. Okay, so again, to extend this, we should remember one thing that ICMP is not directly used by application, but when a TCP IP stack of OS that is being used for triggering a connection, there it checks the destination by ICMP packet. Okay, so we can that like in case our objective is only to check the destination reachability, there we can directly use ICMP instead of going through TCP IP. Okay, so we can write our code like this instead of writing HTTP client send async. We can just write the ping, and of course it will not be able to send any packet. For sending any packet or establishing the connection, we definitely have to use the our operating like our fellow uh, platforms send async or the HTTP client mechanisms. Okay, so now that we have solidified our great understanding like what exactly is happening in the whole request lifecycle and how all the important components like subnet, MAC address, DNS, router, our whole internet, everything that comes in play, and also like the components of our IP packets. So now let's I think it's a good time we can jump onto the actual real life application code and start understanding what is happening behind the scene. So this is one of the like a piece of code in Golang which is connecting to google.com via TCP call and print the output. That's all. Okay, this is written in Golang. So you can see over there, like we have imported few libraries that is essential for making this call. What we are doing is here we are making a HTTP client call. Okay, so whenever we are doing HTTP client call, that means it is a TCP client connection that will be created for a TCP connection, and how it will be how it will get the data is it will get the data uh, from in this response object, and in this response body we are going to read it and we are going to print it. So you can see one two three steps are there. In the first step, in that is the application layer, we are just putting a host name, HTTP client is making the request, and then we are processing the request. And the challenge that we are going to take over here is we are going to totally tear it apart from the OS and networking perspective, what exactly is happening. Okay, so we are going to take the OS plus networking plus application framework. All these things we are going to touch upon while dissecting this piece of code, and this will give us crystal clear idea what is happening behind the scene. Okay, so the first thing in this component, like keep this code in mind, what we are doing is we are having a go app, right? So suppose in our operating system memory one go application is running, and what this go app will do is this go app will create a go runtime in the memory, right? So whenever suppose there is a .exe file or a .dmg file, the moment we start it comes to our RAM. Okay, and in the RAM what is active is for a Go app, it will be the Go runtime. Okay, so it will be the Go runtime. So from the Go app, we are going to do a call to something like HTTP GET to our URL. Okay, suppose our URL is something like https www.google.com. Okay, that is what we have written there. So I'm just copy pasting it. So this is our call. Okay, it is taking to the Go runtime, and our Go runtime will be then taken over by operating system. So this is one of the very critical touch point. Let's understand this thing. From the Go runtime, we will go to our OS kernel. Now that is why, like, while at the start of this video I was talking about, like, this video will be kind of linked to our operating system final video, but even if you haven't watched, don't worry, we will try to explain everything here in detail. Okay, so this request will come to the OS kernel, and with a request that, can you tell me that what exactly is the IP that I need to reach out? So then what our OS kernel will do is, OS kernel will then go to the DNS. From the DNS, it will tell you that, uh, okay, for Google, this is the particular, yeah, so there will be another request here, and what it will be responding is, it will be responding the actual IP address. So at first it will respond to, of course, OS kernel, and then from OS kernel it will go to the Go runtime. So suppose it returns something like this, something like 142.250.190.36. Okay, something like this it returns. Now that IP address is being resolved, so we can say that in this phase the IP resolved. Okay, so once the IP is resolved, what Go runtime does is, it will initiate a TCP connection, and it will instruct the OS kernel only to create the TCP connection. It will tell that I want a TCP connection to, I want TCP to this particular address. Okay, so this is a clear cut message it will tell to the OS kernel. Now OS kernel have the actual access to all of the things, like what are the subnets, what are the current host machine IP and whatnot. So this, there are few things that the OS kernel will start checking. Okay, so what it will check, it will at first check whether the IP is in local subnet or not. Okay, is the IP in subnet? It will say ki no, it is not in the subnet. So if not, what it will do is, it will create a request to the ARP that we just discussed few minutes ago, right? So it will broadcast it request to ARP. The moment it gets the answer as no, that the destination IP is not in the subnet, it will do a broadcast to ARP, and it will ask, that give me the default gateway, or to whom should I actually reach, uh, to as my default gateway, the MAC address. It will ask for the, give me the MAC address. That will be the question, because our OS already have the default gateway. Okay, give me the MAC address of the default gateway. So it will then get the MAC address from here. So OS kernel will get the MAC address from here. Okay, I hope it is not becoming overwhelming for you. I'm just trying to go as slow as possible. So now that we have the MAC address, So the next part of our next part is our default gateway, or our router. Okay, so what would happen here is the request that is coming from the OS kernel. Now that OS kernel knows, Go runtime has already told us that it wants to TCP to this step, right? So suppose if I mark this as 1 here, and all this things, we get a positive response here, that we have the MAC address for default gateway. So what our OS kernel would do is, our OS kernel will send the TCP SYN packet to as a Ethernet frame to the default gateway. Okay, so here the OS kernel will come in play, and it will send the TCP SYN. So this TCP SYN is nothing but the actual IP packet that we are sending. Okay, so this TCP SYN, we can just think it like that this itself is the IP packet. Okay, so once it reaches to the default gateway, what would happen from there is it will forward it to the next hop. So now we are in the default gateway. So from default gateway, it will take it to the internet. So default gateway or the router also we can interchangeably tell. So it will take us to the internet, and this internet will then keep on sending the packet to the next hop. So default gateway, this TCP send, it will send to the here, and it will keep on sending to the next hop. So I will write it like this way: next hop iteration. So it is the same iteration that we just discussed over here, that what will keep on happening. Okay, from the physical data link network and wire plus router, everything will come together, and the message will keep on traveling, and then it will go to the final Google server. Okay, so I will just write this thing here as well for our better understanding. Okay, so now it goes to the Google server, and then from Google server, what happens is, like, it will just keep on sending the response in a happy path manner. Like, it will keep on sending to the router at first, and then the router will forward the request to, like, how it happens is it will send to our default gateway at first, and then from default gateway it will come to our operating system kernel, and our operating system kernel then put it to this application. So there are some other furthermore stuffs do come into the play from the OS kernel perspective. Not going into the details because those are being covered in with super granularity in our operating systems last video. Okay, so this is the seemingly innocent call that we are making. This HTTP GET, what the runtime has done is, runtime has made a call to the OS kernel with all of its power. OS kernel then manages the whole communication, or initiates the whole communication, I would say. And once this communication is being done, as you can see, uh, at the end it comes to the runtime, and yeah, the last step would be it will coming back to the app. Okay, so if you are an application engineer, and if you at any point of time have created network calls or network connections, or any simple HTTP request calls, be it in C Sharp, Node.js, Python, Java, anywhere. So this is the amount of things that goes behind the scene, uh, which is kind of completely abstracted away by the framework, by the network, like by our runtime frameworks, by the operating system, by the actual network layers. So now, again, we will try to, from the application engineer perspective, we will try to solve few more questions. Okay, so suppose I'm giving you one use case here. So let's cover some more real life use cases now. Okay, so suppose we have a service, okay, like our own homegrown service, and we are calling some kind of a third party. So just for the argument's sake, think we are calling something like PayPal. Okay, so PayPal is a complete third party to us, and what we are doing is we are making some payment request calls every time. Now everything is going smooth. Most of the things are going smooth. What is happening is in every 1 hour, okay, for 2 3 minutes, w- we see a very high latency for few requests. Okay, so like it is not really happening consistently. The problem statement is like for 2 3 minutes we are experiencing very high latency means like suppose the it should return within 500 milliseconds. Instead of that, it is taking probably 10 seconds to respond. Okay, like this is expected or even the average, whereas the 10 seconds, like this is like for that 2 3 minutes, it is becoming the 10 seconds. Okay, so uh, the first thing, how we are going to diagnose it. So the first thing is definitely we are going to look into the log, and in the log, suppose I'm giving you one more thing, that we see that when we are doing our http post calls, so http.post or http client.post, some call we are doing and some post requests are going on. Post request is basically creating a payment request in the PayPal. So we see that in our application end, when we are making this post call, after this post call, all this 10 seconds time it is taking. So that definitely means that there is no problem, there is no issue in application end. Because if in the application end there would be some issue, before http client.post, during some processing only we would have got the issue, but we are getting the moment we are creating the TCP connection or we are sending the packet. After sending the packet we have to wait, right? So that means something is happening in the network. Now what are the things that might happen? So now there are so many use cases that might come, right? So as we have been discussing, there can be issue in DNS resolution. For some reason, like it is unable to reach our DNS, the DNS server that it wants to get. So during TCP handshake, maybe some time it is taking because at the server end it is not sending the acknowledgement back in a timely manner. Okay, so then again what might happen is like the tls TLS handshake, or the transport layer security negotiation that happens. Maybe the transport layer security negotiation is not happening properly. It is taking way more time to understand the private key, public key. Also there are something might happen at the server end, that it might like we are sending too many requests maybe for some time, or a request spike is happening at that point of time, so it is queuing or rate limiting. It is queuing or rate limiting our requests. Okay, so and also there are something called throttling. Throttling means it is quite similar to rate limiting but not exactly is that. Throttling means like it is not stopping our request, but making sure that our request doesn't get its full bandwidth. So suppose it is giving a channel of 10 mbps, it will return the data in some kbps speed. Okay, so all these things can be our issue. So this is one of the very key takeaway. Why? Because you see, in this use case, in the application end nothing have happened, but the application got the problem. So when we start diagnosing the problem, we know that we have to go to the network team. We have to ask them that go through your network logs, compare the DNS resolution time, compare the TCP handshake uh, time with the actual requests which are not taking any time, with the request which are taking like almost 10 seconds of time, like the one that is taking 500 milliseconds and the one that is taking 10 seconds. Compare all of the time among them, and maybe after that we can come into some sort of a conclusion. Okay. And also from our end, there are things like TCP dump, which we will cover in a in our next video. So TCP dump plus Wireshark we can use. Okay. So this will give us from our side also, like from the application side also, like if we do not have a dedicated or a very good network engineering team who can help us with this, if we go through our TCP dump plus Wireshark for that particular request which are getting delayed, we will get all this informations there. Okay. So this is one of the very um, or I would say most common real life use cases that application engineer face in the field, and this is how we can very easily technically tackle it uh, by understanding what exactly happening on this aspects, and what are the tooling we can use. We can use the tooling like TCP dump or the Wireshark by ourselves if there is no networking team is available, or we ourselves is the corresponding network team. Another common scenario you might often face is, suppose there is a certain DevOps team we have. Okay, so what this DevOps guys have done is they have deployed a new rule in the network, and suddenly you will see that all your like DB connection or all your connection to the other microservices might start failing. Okay, so once this change has been done, you might see things like connection refused. So if you see errors like this of connection refused, or like the socket connection timeout, something like that, then of course something is something problematic happening around the rule. So this is one of again one of the very common use case. What happens is that, like the DevOps, they generally deploy some service and they create a new rule, or they update their own patch version of the operating system, and then they forget to add a certain uh, control list. So whenever we are seeing this kind of connection refuse sort of a thing, then probably our DevOps or the networking team are the one who have made the changes, and because of that, that connection refused is being impacted. So if I tell it more organically, what exactly happening is the TCP is sending the SYN. Okay, the one that we saw over here, TCP SYN is being sent, but the SYN is not reachable to the default. After the default gateway, it is not reachable to the internet. So the TCP SYN after this level, maybe in some of the hop or in some of the station, it is totally being refused. So that means some configuration around those hops has been changed. Okay, so TCP SYN is failing, like whenever we are getting a connection refused. Again, connection timeout, uh, sorry, failing. Again, connection timeout and the connection refused are different. So connection timeout means like we are making some kind of a request to the database. Okay, and the database is processing, and then it gives you the timeout, probably like within 10 seconds or the stipulated X seconds, it is not responding to that. So we have to understand that connection timeout or the connection refused is totally different. Connection timeout is application issue, whereas connection refused is not. Okay. So I think with all the real life problems that we have discussed, plus the actual detail of the connections, how exactly the whole how exactly a connection is being initiated, how it travels, how our data travels through the actual internet, you got a good idea if you have come till this point. So in my next video again, I will probably go further deep down into TCP, UDP, and into the other modules, and also I will try to cover things like via Wireshark or via other toolings, how we can actually diagnose a few of the network issues. So see you in my next video. Stay awesome. Bye.